Alright, so in this video we're going to look at some extension problems based on Hooke's law and actually look at applying them to real materials and see how it's useful to model how solids behave. So the bonds between atoms in a material act very much like little springs, and what we're going to do is actually calculate the size of the force constant by using the rules that we've seen before. So first of all, we're given the spacing of atoms is 2.56 times 10 to the minus 10. How many atoms will fit in a 1 millimeter length? So in order to solve this, I'm assuming when we're told what the spacing is, that's the distance between centers. So we're not going to have to think about the actual volume or size of the atoms themselves. Okay, so that's an assumption I'm making here. But once we've done that, we can figure out how many there are by doing the length, which I've converted into meters so that they're both in the unit of meters, divided by this spacing, and that gives us this value of 3.91 million atoms, so quite a lot. So if we arrange them in a square pattern, how many atoms would there be in an area of 1 millimeter squared? Well, 1 millimeter squared is 1 millimeter by 1 millimeter. So essentially all we have to do is square the value that we've just obtained. Because if there are 3.9 million in 1 millimeter, there are 3.9 million by 3.9 million in a millimeter squared. So we get this number of atoms in a millimeter squared. Okay. So a specimen of copper is half a meter long, has a cross-sectional area of 1 millimeter squared. When a force of 1000 is applied to the copper wire, it stretches by 4.27 millimeters. If every atom in the layer is connected to another atom in the layer above, and the layers have a spacing, again the same value we've had before, how many layers are there in a length of 0.50? So we're going to use a similar strategy to what we've done before. Assuming the spacing is between the centers, we're going to do the distance divided by the spacing, and then we get that there are 1.95 billion layers of atoms in this material. So the whole thing has stretched by 4.27 millimeters, so each of those little layers has going to be stretched by 2.19 times 10 to the minus 12 by doing this calculation. That's the individual extension. And then, what is the combined spring constant of all the bonds joining two layers of copper atoms? Well, we know the force that's applied, and we know the change in length, so we can just use the mathematical form of Hooke's law to solve this. We rearrange it, do F divided by L, and that gives us a value of 4.57 times 10 to the 14 newtons per meter. So a massive spring constant here, but that's between a lot of bonds. So springs in parallel all add together. So what we're going to do is we're going to divide that number by the number of atoms in a layer, because each of those is making a bond with the next layer. So there were 1.53 times 10 to the 13 bonds acting in parallel, because there's that number of atoms in a layer. So we're going to take our spring constant divided by the number of bonds, and that comes out as 30 newtons per meter, a very ordinary looking spring constant. And actually, to put it in context, if you measure the spring constant of the springs we typically have in a lab, they're somewhere about 20-25, so a very similar order of magnitude to an individual bond in a material, so you can see how strong each of these bonds is, which is why they're all locked very much together in a solid, and they're very difficult to extend or change the length of.